Now we have to find the equivalent resistance across the phase diagonal. The given cube have the vertex A, B, C, D, E, F, G, H. We take one of the phase, say A, B, C, D. So the vertex of the phase diagonal are A and C. So current is entering at A and coming out at C. Now we mark this A with potential VA and this C at potential VC. Here current I is divided in three parts. In the branch AB and AD, these are equal because of the symmetry of the cube across the phase diagonal. So it is I1 say, then remaining current is I minus 2I1, which will flow in third branch AE. By symmetry, we can say that at point C, current R incoming is I1, it is I2, and third one is I minus 2I1 by 2. Now, we can use the formula I equal to V by R. If resistance and current are same, then potential difference will be same. And because potential at A is VA and D, this branch AD and AB have same current, so potential at D and B will be same. Suppose this is V1. Similarly, in branch BC and BC, because of the potential difference is same, current is also same. When I minus 2I1 reaches at point E, it gets two symmetric branches through which same current will flow, and this current is I minus 2I1 by 2. I minus 2I1 by 2. So suppose the potential at this point E is V2. So potential difference across EH and EF will be same. That means we can say this H and F are having the same potential, say V3. And this B is having the potential, suppose V4. So this current I minus 2I1 by 2 passes through V3 to V4, I minus 2I1 by 2, and this branch is also having the current I minus 2I1 by 2. So this branch DH and BF are having no current, so we can remove these two branches. So effectively, we can draw this figure using the potential. This is the point A, which is at potential A, and point C, which is at potential VC. So between A and C, there is a point which having the potential V1, and from VA to V1, there are the two resistors. So we can say these two resistors or two edges are in parallel. Similarly, from V1 to VC, there are again two resistors. Then from A, there is a point E, which is at a potential V2, which is connected through a edge of the resistor R. So we can say this resistor R is connected with the edge E having the potential V2. And similarly, we can say that this C, which is connected at this point, which is having the potential V4, this is also having the resistor R. From V2 to V4, we have two branches, one from E to H and H to G. And this branch is already removed because there is no current. So we can say EH and HG are in series. So we can write it is, this is the one of the series. This is R, this is R. Another one is EF to FG. This is again in series because FB is having no current, so removed. And these two are in series, and effectively these two branches are in parallel, which are having the resistors in series. So we can find effectively the equivalent resistance by simplifying this network. Therefore, we can write this is A, this is C. So these two resistors R and R, so effectively they becomes R by 2. This is V1 and another one is also R by 2. Then there is a resistor R, there is a resistor R, and after that from V2 to V4 we have two branches each having RR in series. So effectively we can write this is one of the branch, this is another branch, this have resistor 2R, this has resistor 2R. These 2R in parallel, so effectively their resistances are. This R by 2 in series, so their effectively resistances are. So we can also redraw this simplified circuit as this is the point A and C across which we have to find the equivalent resistance. Here the resistance is R, there is a resistance R, there is a resistance R, and there is a resistance R. So now these three resistors are in series. So we can draw this as this is AC, R, and this resistance each 3R. And now this R and 3R are in parallel. Therefore, we can say that R equivalent is equal to R into 3R by R plus 3R. That is equal to 3R square by 4R or 3R by 4. So we have found that equivalent resistance is equal to 3R by 4 across the phase diagonal.